There's something downright humbling about looking up at the night sky. Those countless pinpricks of light, each one a sun like our own, scattered across an ocean of darkness so vast it defies comprehension. And yet, for all we've learned about the cosmos, the truth is we've barely scratched the surface. The universe is teeming with mysteries that refuse to fit neatly into our textbooks, phenomena so bizarre they challenge everything we think we know. Today, we're setting off on a journey to explore 30 of the most mind-bending galactic enigmas ever discovered, cosmic puzzles that leave even the brightest astronomers shaking their heads in wonder. Picture this: black holes that shouldn't exist, stars that vanish without a trace, galaxies spinning in ways that defy the laws of physics. These aren't plot twists from a sci-fi novel. They're real, documented events happening right now in the depths of space. Some of these mysteries might hold the keys to understanding dark matter, the fabric of reality, or even the ultimate fate of the universe itself. Others, well, they're just gloriously unexplained, and that's the beauty of it, because every time we think we've got space figured out, the cosmos throws us another curveball, reminding us how much there still is to discover. So if you've ever stared up at the stars and felt that tug of curiosity, that burning question, what else is out there, then you're in exactly the right place. This isn't just a list, it's an expedition into the unknown, a tour of the cosmic anomalies that keep scientists awake at night. From eerie radio signals to structures so enormous they rewrite the rules of astronomy, we're about to dive deep into the weirdest corners of the galaxy. Buckle up, because by the time we're done, you'll never look at the night sky the same way again. It was just another quiet night at Ohio State University's Big Ear radio telescope back in August 1977, with astronomer Jerry Amon scanning the skies for any unusual signals from the cosmos. Then, out of nowhere, the instrument spiked a burst of radio waves so intense, so unnervingly precise, that Amon circled the data printout in red pen and scribbled a single word next to it: wow. That fleeting 72-second signal, never heard again despite decades of searching, remains one of the most tantalizing mysteries in astronomy. What made the wow signal so extraordinary wasn't just its strength, 30 times louder than the background noise of space, but its frequency. It hit exactly 1,420 megahertz, a silent channel where natural cosmic phenomena rarely transmit. Scientists call this the water hole, a quiet band between hydrogen and hydroxyl radio waves that hypothetical alien civilizations might use to broadcast their presence. The signal's narrow bandwidth and precise frequency suggested artificial origin, sparking debates that still rage today. Could it have been a passing comet reflecting radio waves in a strange echo? Unlikely. No known comets were in that region of space at the time. A secret military satellite, declassified records show nothing that matches. Or, as some daringly speculate, was it a fleeting hello from another civilization, a cosmic flare that vanished before we could answer back? The truth is, after nearly 50 years, we're no closer to solving the puzzle. The wow signal stands as a haunting reminder that the universe might be shouting at us, but we're still learning how to listen. Imagine holding a snow globe, one where you can clearly see the swirling flakes, but the liquid inside is completely invisible. Now picture the entire universe working that same way. That's essentially the puzzle of dark matter, an invisible something that makes up over a quarter of everything in existence, yet refuses to show itself no matter how hard we look. We know it's there because galaxies spin faster than they should, their outer stars whipping around like a merry-go-round with an unseen hand pushing them. Without dark matter's gravitational glue, galaxies would fly apart, yet we've never directly caught a glimpse of it. So what could it be? The leading suspects sound like something from a physicist's wish list: WIMP, or weakly interacting massive particles. These hypothetical heavyweights would barely interact with normal matter, hence why they've dodged detection. But their sheer mass could explain the gravitational tug we observe. Then there are actions, ghostly ultralight particles that might flit through space like cosmic fireflies. Some theories even suggest dark matter could form exotic structures like invisible, dark stars or shadow galaxies right under our noses. Yet after decades of hunting with underground labs, particle colliders, and space telescopes, we've got nothing but silence. The more we learn, the stranger it gets, like recent findings that certain galaxies seem to lack dark matter entirely, throwing a wrench into our models. Is dark matter a single substance or a zoo of different particles? Does it interact with itself in ways we can't yet see? Every dead end in the search just deepens the mystery, proving that most of the universe isn't just hiding in the shadows it's made of them. If dark matter is the universe's invisible scaffolding, then dark energy is its ghostly accelerator, a force so baffling that even the scientists who discovered it initially doubted their own data. Here's the puzzle: not only is the universe expanding, but that expansion is speeding up, as if some unseen hand is pressing harder on the cosmic gas pedal with every passing second. And this isn't some subtle effect. Dark energy makes up a staggering 68% of the universe's total energy budget, dwarfing everything else, including dark matter. Yet despite its dominance, we have no idea what it actually is. The story starts in the late 1990s, when two teams of astronomers were studying distant supernova to measure how fast the universe's expansion might be slowing down. Instead, they found the opposite. The light from these exploding stars was fainter than expected, meaning space itself was stretching faster over time. The implications were staggering. Either Einstein's theory of gravity was wrong on cosmic scales, or something far stranger was at work. That something earned the placeholder name dark energy, and it's been upending physics ever since. One leading explanation harkens back to Einstein's old cosmological constant, a sort of built-in energy of empty space itself. Quantum physics suggests that even a perfect vacuum should fizz with particles popping in and out of existence, potentially generating a repulsive force. Trouble is, when scientists crunch the numbers, the predicted strength of this vacuum energy overshoots reality by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst mismatch in science history. Other theories propose dark energy might be a dynamic field, evolving over time like an invisible fifth fundamental force. Some even suggest it's evidence we're seeing the shadow of parallel universes in a vast multiverse. But every hypothesis comes with its own contradictions. If dark energy changes strength, why haven't we detected its fluctuations? If it's truly constant, why did it only overpower gravity's pull about 5 billion years ago? The more we learn, the clearer it becomes. Dark energy isn't just a mystery. It's a glaring signpost that somewhere our understanding of reality has gone profoundly off track. What makes dark energy so humbling is how it forces us to confront the limits of human knowledge. Here's a force shaping the entire fate of the cosmos, whether galaxies will eventually rip apart in a big rip or fade into cold isolation, and we can't even say if it's a property of space or something entirely new. It's the ultimate cosmic irony. The universe's dominant ingredient is also its least understood, and unless we crack this puzzle, we might be missing the biggest chapter in the story of everything. One of the most electrifying mysteries in modern astronomy lasts less time than it takes to blink: fast radio bursts, or FRB. These cosmic flashes pack more energy than our sun emits in 80 years into a burst that vanishes in milliseconds. When the first one was detected in 2007, buried in archival data from the Parkes Radio Telescope in Australia, astronomers assumed it must be some fluke, a glitch in the instruments, or a nearby microwave oven accidentally leaking interference. But then more bursts came, some from billions of light years away, their radio waves stretched by the expansion of the universe. Whatever was producing these signals wasn't just powerful, it was happening across the cosmos. The strangest part, most FRBs are one-off events like cosmic firecrackers that go off once and never repeat. But in 2016, astronomers caught something revolutionary, a repeating FRB coming from a tiny galaxy 3 billion light-years away. This wasn't just a random explosion. Something out there was capable of firing multiple bursts, sometimes in predictable patterns. Suddenly, the theories got wilder. Could these be the afterglow of colliding neutron stars? The death cries of evaporating black holes, or as some have dared to suggest, bursts from alien propulsion systems, harnessing unimaginable energy to push light sails across galaxies. The leading suspect today is a type of neutron star called a magnetar, a city-sized corpse of a dead star with a magnetic field so strong it could wipe a credit card clean from halfway across the moon. When magnetars experience starquakes, cracking under the strain of their own magnetism, they might unleash these radio tsunamis. In 2020, astronomers got their best evidence yet when a magnetar in our own galaxy fired off an FRB-like burst just as telescopes were watching. Yet the puzzle is far from solved. Some FRBs are too energetic to fit the magnetar model, and the repeating ones defy conventional explanations. Then there's FRB 190520, a burst from a galaxy 7 billion light-years away that pulsed with a rhythm eerily similar to a heartbeat. Whether these are natural cosmic lighthouses or something even more extraordinary, one thing's clear: FRBs are rewriting the rules of high-energy astrophysics, proving that the universe still holds surprises that can light up the sky and our imaginations in the blink of an eye. In the constellation Cygnus, there's a star that refuses to play by the rules. KIC 8462852, better known as Tabby's star, named after astronomer Tabetha Boyajian, who first spotted its strange behavior. At first glance, it looks like any other sun, but when the Kepler Space Telescope trained its eyes on it, the data revealed something shocking. This star didn't just dim slightly when planets passed in front. It plunged in brightness by up to 22% in bizarre, irregular dips, as if something enormous and misshapen were blocking its light. And these weren't fleeting shadows. Some lasted for days, even weeks, with no rhythmic pattern to explain them. The first theory tossed around: a massive swarm of comets, thousands of them, trailing dust and debris that could intermittently obscure the star. But even that stretched credibility. No natural comet family we've ever seen could create such extreme, erratic dimming. Then things got weirder. Historical data showed the star's overall brightness had been fading over the past century, dropping by a staggering 14%. Stars don't just dim like that unless they're dying, and Tabby's star is very much alive. That's when the wilder hypotheses took off. Could this be evidence of an alien megastructure like a Dyson swarm, a colossal array of energy-harvesting satellites built by an advanced civilization? The idea wasn't entirely science fiction. Astronomers have seriously debated how to distinguish artificial structures from natural phenomena. But before anyone could get too excited, follow-up studies found no telltale signs of technology like laser communications or waste heat. So what's really going on? Recent observations suggest a more plausible yet still bizarre answer: a shattered planet or moon torn apart by the star's gravity, leaving behind a chaotic disk of dust and debris that occasionally drifts into our line of sight. Even so, the numbers don't quite add up. The amount of material needed to explain the dimming is far greater than anything we've seen in other star systems. Tabby's star remains one of astronomy's greatest enigmas, a cosmic Rorschach test where every new observation seems to raise more questions than answers. Whether it's a natural phenomenon we've yet to understand or something even more extraordinary, one thing's certain: this star is a reminder that the universe still has tricks up its sleeve, and sometimes the most ordinary-looking objects hide the most astonishing secrets. Deep in the cosmic shadows, beyond the familiar sprawl of our own galaxy, something colossal is pulling. An invisible force dragging entire galaxies, including our own Milky Way, toward a point in space we can't even see. Astronomers call it the Great Attractor, and it's one of the universe's most frustrating mysteries, lurking in what's known as the Zone of Avoidance, a region of sky obscured by the thick dust and stars of our galaxy's central bulge. Imagine trying to study a distant city through fog, but the fog is made of billions of stars, and the city holds the key to understanding why everything around you is moving in the same eerie direction. The first clues emerged in the 1970s when astronomers noticed something odd about the motion of nearby galaxies. Instead of drifting uniformly with the expansion of the universe, they were all streaming toward a single patch of sky near the constellations Centaurus and Hydra, as if caught in a cosmic current. Calculations suggested this mysterious pull came from a concentration of mass equivalent to tens of thousands of Milky Ways, all clumped together somewhere around 250 million light-years away. But when telescopes turned toward that patch of space, they found nothing, or rather nothing they could clearly see. Our own galaxy's dust and gas were blocking the view, leaving the Great Attractor hidden in plain sight. Modern X-ray and infrared telescopes have since pierced some of that obscuring veil, revealing a mind-bending truth. The Great Attractor isn't just one massive object, but likely the heart of the Laniakea supercluster, a sprawling web of galaxies spanning 500 million light-years, with our Milky Way sitting on the fringes like a suburban cul-de-sac. At its center lies the Norma cluster, a dense knot of galaxies and hot gas exerting a gravitational pull so immense it shapes the motion of everything around it. But here's the twist: even Laniakea seems to be moving, tugged toward something even larger and more distant, the Shapley supercluster, a titanic structure 800 million light-years away that may be the true apex of this cosmic hierarchy. The challenge now isn't just mapping what's hidden behind the zone of avoidance, but untangling the universe's large-scale structure itself. Every time we peel back one layer of this gravitational mystery, we find another, deeper pull, a cosmic Matryoshka doll of invisible forces. And that's what makes the Great Attractor so humbling. It's not just a destination, it's a signpost pointing to how little we truly understand about the forces sculpting the universe on the grandest scales. One thing's certain: wherever this cosmic river is leading us, the journey promises to rewrite the map of everything we know. There's a silent feeding frenzy happening all around us in the cosmos, galaxies locked in an endless dance of consumption and destruction. What looks like a serene snapshot of spiral arms and glowing nebulae is actually a battlefield where the biggest players grow by swallowing their smaller neighbors whole. This process, known as galactic cannibalism, isn't science fiction. It's written into the very fabric of our Milky Way's history. Take a close look at the night sky and you'll spot the aftermath of these cosmic feasts. Dense streams of stars, stretched like taffy across thousands of light-years, trace the paths of smaller galaxies ripped apart by our own Milky Way's gravity. One of the most obvious victims is the Sagittarius dwarf spheroidal galaxy, a tiny satellite that's been orbiting and being devoured for billions of years. As it spirals inward, our galaxy's tidal forces have torn it into a looping stellar river that wraps around us like a celestial serpent. But this isn't just destruction, it's recycling on a galactic scale. Every swallowed galaxy adds new stars, gas, and even dark matter to the Milky Way's growing bulk. Andromeda, our nearest spiral neighbor, is an even more voracious predator. Hubble telescope images reveal its halo littered with the remnants of at least 24 devoured galaxies, some as recently as a few billion years ago. One victim, a galaxy called M32, survived as a bizarre compact elliptical, stripped of its outer layers but with a supermassive black hole still lurking at its core, a silent witness to its near demise. Some of the most striking evidence of galactic cannibalism comes in the form of shell galaxies, odd structures where concentric rings of stars ripple outward like the layers of an onion. These are the ghosts of smaller galaxies, their stars flung into precise orbits during the slow-motion collision. The best-known example, galaxy NGC 4742, looks like it's encased in shimmering cosmic bubbles, each shell marking a different phase of its cannibalistic feast. But here's the twist, even the devourers are on the menu. The Milky Way and Andromeda are hurtling toward each other at 250,000 miles per hour, destined to collide in about 4.5 billion years. When they merge, their spiral arms will twist into chaos, stars flung into wild new orbits, and their central black holes will eventually spiral together in a gravitational tango that shakes the fabric of spacetime itself. The result, a single, bloated elliptical galaxy some dub Milkomda, a monument to the universe's relentless cycle of creation and destruction. This isn't just a distant future, it's a pattern as old as the cosmos. Galaxy clusters, the largest structures in the universe, grow the same way, with giant central galaxies like IC 1110 acting as gravitational anchors, pulling in dozens of smaller galaxies over eons. The universe, it seems, runs on a simple rule: grow or be eaten. And as we trace the scars of past collisions across the night sky, we're reminded that even the grandest galaxies are just temporary arrangements in an endless cosmic dance. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing billions of stars, most likely orbited by countless planets. Given these numbers, the math suggests extraterrestrial civilizations should be everywhere. So where is everybody? That's the unsettling core of the Fermi paradox, named after physicist Enrico Fermi, who famously posed the question during a casual lunchtime conversation in 1950. If intelligent life is common, why haven't we found a single whisper of its existence? No signals, no artifacts, no visitors. The silence isn't just puzzling, it's downright eerie. One possible answer lies in the concept of the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar communication or exploration. The terrifying implication: if the filter lies in our past, some critical step like the emergence of DNA or complex cells being extraordinarily rare, then humanity might be a miraculous fluke. But if the filter is ahead of us, something that reliably wipes out civilizations before they spread beyond their home system, then our future could be bleak. Nuclear war, runaway AI, environmental collapse, any of these could be lurking in our path, explaining why the galaxy isn't buzzing with activity. Then there's the zoo hypothesis, the idea that advanced civilizations deliberately avoid contact, treating Earth like a protected wildlife preserve. It sounds like science fiction, but consider how humans observe uncontacted tribes today, keeping our distance to avoid disruption. Alternatively, alien societies might communicate in ways we can't yet detect, using neutrino beams or quantum entanglement instead of radio waves. Other theories are even more mind-bending. Maybe intelligence is a dead-end trait, with civilizations inevitably destroying themselves or losing interest in expansion. Or perhaps we're early to the party, born in a cosmic quiet period before life blooms across the universe. The most haunting possibility that we truly are alone, a flicker of awareness in an endless, empty night. The Fermi paradox isn't just an academic puzzle, it holds up a mirror to humanity's place in the cosmos. Every new exoplanet discovered, every silent SETI scan, forces us to confront how little we know and how much wonder or dread might still lie ahead. In the darkest reaches of space, where light takes billions of years to reach us, there are objects so luminous they outshine entire galaxies, quasars. These cosmic beacons, fueled by supermassive black holes, are some of the most energetic phenomena in the universe. Yet the very thing that makes them so brilliant, their staggering distance, also makes them some of the most enigmatic. At the heart of every quasar lies a monstrous black hole, billions of times more massive than our Sun, greedily devouring gas, dust, and even entire stars. As this material spirals inward, friction heats it to millions of degrees, creating a swirling disk of supercharged plasma that blasts out radiation across the electromagnetic spectrum. But quasars aren't just bright, they're hyper-bright. A single quasar can outshine 1,000 Milky Ways, making them visible across cosmic distances that would render ordinary galaxies invisible. What's truly mind-blowing is how old these objects are. The light from the most distant quasars has traveled for over 13 billion years, meaning we're seeing them as they were when the universe was barely 1 billion years old. That raises a staggering question. How did supermassive black holes grow so massive, so fast? Current theories struggle to explain how these cosmic titans could have formed in what amounts to the universe's infancy. Some might have sprouted from colossal, seed black holes left behind by the collapse of the first supergiant stars. Others could be the result of direct collapse primordial gas clouds skipping the star phase entirely and imploding straight into black holes. Then there's the puzzle of redshift. Normally, the farther away an object is, the more its light is stretched toward the red end of the spectrum by the expanding universe. But some quasars don't follow the rules. They exhibit redshift anomalies that can't be explained by simple cosmic expansion. One wild hypothesis suggests these outliers might be ejecting material at near light speeds, distorting their apparent distance. Another theory proposes that we're seeing light bent by gravitational lensing, warped around invisible masses on its journey to us. But quasars aren't just cosmic curiosities, they're time machines. Their light carries chemical fingerprints of the early universe, revealing traces of elements like carbon and oxygen long before stars had time to forge them in abundance. Some even show evidence of gigantic magnetic fields threading through the infant cosmos, clues to conditions we can't replicate in any lab, the most thrilling part. Quasars might hold the key to understanding how galaxies, including our own, were born. Many astronomers believe every massive galaxy went through a quasar phase in its youth, with the central black hole's violent outburst shaping the formation of stars and influencing the galaxy's structure. Today, our Milky Way's black hole is quiet, a sleeping giant, but billions of years ago, it may have been a quasar itself, lighting up the early universe with its fury. As telescopes like the James Webb probe deeper into space, and further back in time, quasars continue to surprise us. Some flicker unpredictably, their brightness changing in ways that defy current models. Others appear to be paired with second quasars, suggesting black hole duels in the cosmic dark. Each discovery peels back another layer, revealing just how little we understand about these brilliant, ancient monsters. One thing's certain, quasars aren't just relics of the past. They're blazing signposts guiding us toward the untold stories of the universe's fiery dawn. Black holes aren't just cosmic vacuum cleaners, they're existential conundrums, shredding not just matter but the very laws of physics as we know them. At the heart of this chaos lies the black hole information paradox, a puzzle so profound it pits quantum mechanics against Einstein's theory of relativity in a battle with no clear winner. It all started with Stephen Hawking's bombshell realization in the 1970s. Black holes aren't completely black. Through a bizarre quantum quirk, they slowly leak energy particles escaping their gravitational grip in what we now call Hawking radiation. Over eons, this drip feed of particles causes black holes to evaporate, vanishing without a trace. But here's the problem. According to quantum mechanics, information, the fundamental blueprint of every particle that ever fell into the black hole, can never be destroyed. Yet Hawking's math suggested it was being erased permanently, a violation of quantum law that sent physicists into a frenzy. Imagine burning a book. The ashes might seem like gibberish, but in theory, every word could be reconstructed if you tracked the exact position of each carbon molecule. Black holes, however, appeared to be the ultimate incinerators, not just burning the book but erasing even the possibility of reading it. This wasn't just an academic debate, it struck at the heart of reality's predictability. If information could vanish, the entire framework of cause and effect might unravel. The controversy sparked decades of competing theories. Some, like the no-hair theorem, suggested black holes were cosmic bald spots, memorializing nothing but mass, charge, and spin. Others, like Leonard Suskind's holographic principle, proposed that information isn't lost but encoded on the event horizon's surface like a celestial hard drive, projected into the universe as the whole evaporates. Then came the firewall's hypothesis, a wild idea that the event horizon isn't a gentle boundary but a searing wall of quantum energy, shredding incoming matter and preserving information through sheer violence. Recent breakthroughs in string theory and quantum gravity have added new wrinkles. Calculations now suggest information might escape via subtle correlations between Hawking radiation particles, like a cosmic game of telephone where the message is passed between photons. Meanwhile, lab experiments with analog black holes made of sound waves or light are testing these ideas right here on Earth. What makes this paradox so thrilling isn't just the theoretical clash, it's the stakes. Solving it could reveal the missing link between quantum mechanics and gravity, the holy grail of modern physics. Every time we think we've pinned down the answer, black holes remind us how little we truly understand. They're not just celestial oddities, they're the universe's most ruthless teachers, forcing us to rewrite the textbooks one paradox at a time. Neutron stars are the universe's ultimate cosmic pressure cookers, stellar corpses so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. But even in their death, these remnants of supernova refuse to go quietly. Every so often, astronomers catch one doing something impossible, speeding up its spin without warning, like a figure skater pulling in their arms, except no outside force is doing the pulling. These sudden jumps, called glitches, have defied explanation for decades, revealing just how little we understand about matter pushed to its most extreme limits. Picture a star more massive than our Sun, crushed into a sphere barely 12 miles wide. The gravity is so intense that protons and electrons fuse into neutrons, creating a substance so tightly packed it verges on becoming a single atomic nucleus. Yet within this unfathomable density, neutron stars hide even stranger secrets. Their crusts are thought to be a crystalline lattice of iron nuclei, 100 billion times stronger than steel, while their interiors may contain exotic states of matter like superfluids, fluids with zero viscosity that flow without resistance. This extreme environment sets the stage for glitches. Normally, neutron stars slow down over time, their rotation gradually bleeding energy as magnetic radiation. But during a glitch, the star's spin rate suddenly increases by a tiny but measurable fraction, sometimes in just seconds. The most dramatic recorded event happened in 2016, when the Vela pulsar, a neutron star spinning 11 times per second, jumped in speed by 1 part in a million. That might sound small, but for an object with the mass of a star, it's like stopping a freight train, only to watch it inexplicably lurch forward on its own. So what's really going on? The leading theory involves a tug of war between the star's rigid crust and its superfluid core. Imagine the crust as a spinning bucket filled with a bizarre, frictionless liquid. As the crust slows down, the superfluid inside initially keeps spinning at its original speed, creating tension. When the difference becomes too great, the superfluid transfers angular momentum back to the crust in a sudden burst, like a sloshing wave hitting the sides of the bucket and giving it a kick. But there's a twist. Some glitches don't fit this model. They're too large, too fast, or followed by prolonged recovery periods. That's where starquakes come in. The crust of a neutron star, under unimaginable strain from magnetic fields and rotation, might fracture like tectonic plates, releasing pent-up energy that briefly changes the star's spin. Others speculate about vortex unpinning, where swirling tendrils of superfluid break free from the crust's grip, transferring momentum in chaotic bursts. The real shocker, some neutron stars show anti-glitches, sudden slowdowns that turn the theory on its head. Could these be signs of material falling back onto the star's surface, or magnetic reconfiguration sapping its energy? The truth is, every glitch we observe forces physicists to rethink the rulebook. These cosmic speed bumps aren't just quirks, they're glimpses into a realm where matter behaves in ways no lab on Earth can replicate. What makes neutron star glitches so mesmerizing is how they bridge the known and the unknown. Each erratic spin change is a message bottled in extreme physics, carrying clues about the fundamental nature of matter, gravity, and perhaps even states of existence we've yet to imagine. And until we crack their code, these ultra-dense enigmas will keep keeping us guessing, one sudden, mysterious leap at a time. There's something deeply unsettling about the universe's baby picture, the cosmic microwave background, or CMB. This faint glow, the afterimage of the Big Bang, should be a random, isotropic tapestry of hot and cold splotches, a testament to the universe's uniformity. But when scientists mapped it with unprecedented precision, they stumbled upon an anomaly so bizarre it earned a name straight out of a sci-fi thriller, the axis of evil. This so-called axis isn't some galactic superstructure, it's an eerie alignment. The CMB's largest fluctuations aren't scattered randomly across the sky. Instead, they're weirdly coordinated with the plane of our solar system, as if the universe itself is giving our little corner of space preferential treatment. That shouldn't happen. The Copernican principle, the bedrock of modern cosmology, insists we aren't special. The universe isn't supposed to care about Earth's orientation. Yet here we are, staring at a pattern that defies expectation. Some researchers argue it's just a fluke, a cosmic coincidence amplified by our human tendency to find patterns in noise. After all, if you toss a coin enough times, you'll eventually get a suspicious streak of heads. But the odds of this particular alignment happening by chance? Less than 1 in 1,000. Others suggest more mundane explanations, like subtle errors in how we subtract the Milky Way's foreground glow from CMB data. Yet, even after meticulous corrections, the axis persists, taunting astronomers like a puzzle missing its final piece. Then there are the radical theories. Could this be evidence of a pre-Big Bang universe, its structure imprinted on space-time like a ghostly fingerprint? Or does it hint at something even stranger, a cosmic topology so convoluted that the universe wraps around itself, creating the illusion of alignment? The most unsettling possibility, that we're seeing the gravitational shadow of a neighboring universe pressing against ours like a hand against frosted glass. Whatever the truth, the axis of evil is more than a statistical oddity. It's a direct challenge to our understanding of the universe's fundamental fairness. If the cosmos really does have a preferred direction, it forces us to rethink everything from dark energy's distribution to the very nature of infinity. Until we crack this enigma, one thing's certain: the universe's baby picture just got a lot more mysterious. In the vast emptiness of interstellar space, far beyond the orbits of Pluto and the Kuiper belt, 2 robotic pioneers were quietly rewriting the laws of physics, or so it seemed. The Pioneer 10 and 11 probes, launched in the early 1970s to study the outer solar system, became the center of one of astronomy's most perplexing whodunits. Decades after their primary missions ended, as they coasted toward the stars, scientists noticed something bizarre. Both spacecraft were slowing down slightly more than predicted, as if an invisible hand was gently tapping the brakes. This tiny discrepancy, just 10 billionths of a meter per second squared, became known as the Pioneer anomaly, and it would haunt physicists for decades. At first, the leading suspect was mundane: heat. The probe's plutonium-powered generators constantly radiated warmth, and some scientists argued that infrared photons bouncing off the spacecraft's antenna dish could create just enough recoil to explain the deceleration. Others pointed to tiny gas leaks from thruster systems or even the subtle pressure of cosmic dust. But when researchers crunched the numbers, none of these explanations fully accounted for the anomaly's precise, consistent drag, a force that seemed to act uniformly on both probes despite their different trajectories. That's when the theories got interesting. Could this be the first detectable hint of modified gravity, a sign that Einstein's general relativity breaks down at extremely weak accelerations? Some researchers proposed theories like Mund-modified Newtonian dynamics, suggesting gravity behaves differently at the faintest edges of the solar system. Others speculated about unseen dark matter clumps or even exotic physics like vacuum energy effects. For a brief, thrilling moment, it seemed humanity might be on the verge of discovering a fundamental flaw in our understanding of the cosmos. Then came the plot twist, when scientists analyzed trajectory data from later missions like the Cassini probe to Saturn and the New Horizons spacecraft speeding toward Pluto. They found no trace of the Pioneer effect. If new physics were at play, why weren't other spacecraft affected? The mystery deepened further when researchers realized the anomalous acceleration wasn't constant. It seemed to diminish slightly over time. Detailed thermal models could now explain more precisely. After years of debate, the consensus settled on heat radiation as the primary culprit, though some residual questions remain. What makes the Pioneer anomaly so enduringly fascinating isn't just the anomaly itself. It's how perfectly it illustrates science's self-correcting nature. A tiny discrepancy, painstakingly measured across billions of miles, sparked a decades-long detective story that forced us to question everything from spacecraft engineering to the fabric of spacetime. And while the answer turned out to be more ordinary than some had hoped, the legacy lives on. Future missions, like the proposed interstellar probe, will carry instruments designed to measure such effects with unprecedented precision, because in the quest to understand the universe, even the smallest unexplained drift might be the first whisper of something revolutionary. On October 19, 2017, astronomers spotted something streaking through our solar system that shattered every expectation, a cigar-shaped object moving so fast it could only have come from interstellar space. Named Oumuamua Hawaiian for Scout, this mysterious visitor became the first known immigrant from another star system, and its bizarre behavior sparked a debate that still rages today. At first glance, Oumuamua seemed like a simple space rock, albeit an unusually elongated one stretching perhaps 800 meters long but only 80 wide, tumbling end over end like a cosmic drill bit. But as scientists tracked its trajectory, something didn't add up. Instead of slowing under the sun's gravity as expected, Oumuamua accelerated as if pushed by an unseen force. Natural explanations pointed to comet-like outgassing icy material vaporizing in sunlight, creating a faint jet that nudged the object forward. But here's the catch: no visible coma or tail, the usual fingerprints of outgassing, could be detected. That's when hypotheses took a wild turn. Harvard astronomer Avi Loeb famously suggested Oumuamua might be artificial, a light sail propelled by starlight, perhaps even debris from an alien civilization. The idea wasn't entirely far-fetched. Human projects like Breakthrough Starshot aim to send similar wafer-thin probes to nearby stars. Yet critics countered that nature could produce such acceleration without extraterrestrial engineering. Maybe Oumuamua was a hydrogen iceberg, its invisible vapor jets leaving no trace, or a fractal-like dust bunny of porous material, so light that solar radiation alone could push it. The deeper mystery we'll never know for sure. Oumuamua raced out of telescope range before detailed observations could settle the debate, leaving behind tantalizing but incomplete data. Its uniqueness torments astronomers. Was it a fluke or the first of many? Subsequent interstellar visitors, like the clearly cometary Borisov in 2019, only deepened the puzzle by behaving so ordinarily. What makes Oumuamua unforgettable isn't just its strangeness, but what it represents. A cosmic postcard from realms we've barely begun to explore, challenging us to rethink what's possible. Whether ancient ice fragment, alien artifact, or something even stranger, this interstellar enigma proves the universe still has surprises hurtling right through our backyard. The Moon today is a quiet, airless world, its surface frozen in time, its core long since cooled. But ancient rocks tell a different story. Samples brought back by Apollo astronauts revealed something astonishing. Our Moon once had a magnetic field, perhaps even stronger than Earth's at times. For a world just 1% of Earth's mass, this shouldn't be possible. Magnetic fields require churning molten metal cores, and something so small should have cooled and solidified billions of years ago. Yet the evidence is etched in lunar rocks like cosmic hieroglyphs, their minerals aligned by magnetic forces that vanished eons ago. How could such a small body sustain this planetary scale phenomenon? One leading theory points to a dynamo effect, a molten iron core swirling like a cosmic whirlpool, generating magnetism as it moved. Early in its history, the Moon's core might have been kept molten by tidal heating, its interior stretched and kneaded by Earth's gravity like putty. But here's the problem. Models suggest this heat would have faded within a few 100 million years, while lunar rocks show magnetism persisting for over 1 billion. That's where the asteroid impact theory comes in. The ancient Moon was a punching bag, battered by collisions so violent they could have supercharged its core. Imagine a city-sized rock slamming into the lunar surface with enough force to send seismic waves rippling through the interior. These impacts might have stirred the core like a spoon in a cup of coffee, briefly reigniting the dynamo. Some scientists even speculate that a single colossal impact could have tilted the Moon's core off kilter, creating imbalances that sustained magnetic activity far longer than expected. But there's a twist. Recent studies of moon rocks suggest the field didn't fade gradually. It flickered, surging and collapsing in unpredictable bursts. This has led to even wilder ideas like core crystallization. As the Moon's molten core cooled, solidifying iron might have released latent heat and light elements, creating buoyant plumes that briefly revived convection. Picture a lava lamp where rising blobs of molten metal generate magnetism in sporadic pulses. The implications stretch far beyond lunar science. If small bodies like the Moon once had magnetic fields, perhaps Mars did too, not just in its youth but in sporadic revivals. Even asteroids like Vesta might have hosted fleeting magnetism, rewriting our understanding of how cosmic shields form and fade. And if impacts really can jump-start planetary cores, it suggests magnetism isn't just about size, it's about violence, timing, and a bit of cosmic luck. What makes this mystery so compelling is how it forces us to rethink planetary evolution. The Moon isn't just a dead rock, it's a fossilized record of planetary adolescence, its magnetic scars hinting at a past far more dynamic than its silent surface lets on. Every new lunar mission, every speck of dust analyzed, brings us closer to understanding how something so small could once have thrummed with invisible cosmic energy. One thing's clear, in the story of the solar system, even the quietest characters might have had the loudest beginnings. Most of the cosmos is a tapestry of galaxies, woven into vast clusters and filaments, but in the constellation Boötes, there's a hole in the fabric. Not just any hole, but a yawning chasm of nothingness so vast it could swallow thousands of Milky Ways whole. This is the Boötes Void, a spherical desert of space stretching 330 million light-years across, where galaxies are so scarce that if you stood at its center, you'd see almost nothing in every direction. That shouldn't exist. According to our best models of cosmic evolution, voids this massive simply can't form naturally, yet here it is, a cosmic conspiracy of emptiness. The mystery isn't just its size, it's what's missing. In a typical region of space that large, you'd expect at least 2,000 galaxies. the Boötes void has 60. That's not just sparse, it's practically uninhabited, like finding a single grain of sand in an Olympic-sized swimming pool. Even stranger, the few galaxies that do lurk here aren't arranged randomly. They clump along faint, thread-like structures, huddling together as if seeking safety in numbers. Astronomers call them void galaxies, and they're some of the loneliest, most peculiar star systems in existence. Isolated from the bustling galactic crowds, these outcasts evolved differently. With fewer galactic neighbors to cannibalize or collide with, void galaxies often remain small and pristine frozen relics of the early universe. Some glow with an eerie blue hue, their star formation unquenched by the violent interactions that shape cluster galaxies. Others are ultra-diffuse, ghostly systems so faint they're nearly transparent, their stars scattered like dust in a sunbeam. But how did the void itself form? One theory suggests it's the aftermath of an ancient, unimaginable collision, not between galaxies but between entire universes. In the bubble universe hypothesis, our cosmos might have bumped into a neighboring one in the multiverse, their meeting creating a dead zone where matter was pushed aside like cosmic flotsam. Others propose it's evidence of a supervoid, a region where dark energy dominates, repelling galaxies like oil repels water, the most haunting possibility. That the Boötes void isn't empty at all, but filled with something we can't see. Dark matter, exotic particles, or even the gravitational scars of long-vanished civilizations could lurk there, invisible to our telescopes. Whatever the truth, this great cosmic blank spot forces us to confront an uncomfortable reality. Our maps of the universe might be missing more than we ever imagined. After all, when you stare into the void, sometimes the void stares back not with eyes, but with questions we're only beginning to ask. For decades, a shadow has orbited Earth, not in the darkness of space, but in the twilight zone between fact and legend. Meet the Black Knight satellite, an object that conspiracy theorists claim is a 13,000-year-old alien probe silently watching humanity, while scientists dismiss it as a jumble of misidentified space junk and overactive imaginations. The truth, it's stranger than either extreme. The myth began in the 1950s when newspapers reported that the U.S. Air Force had detected an unknown object in polar orbit, an impossible feat for human technology at the time. Stories swirled that Nikola Tesla had intercepted its signals decades earlier, and that ancient civilizations carved its likeness into their art. By the 90s, the legend had crystallized, a sleek, black, otherworldly satellite, its origins lost to time, circling Earth as a silent sentinel. Reality, as usual, is more mundane but no less fascinating. The infamous Black Knight image that spread across the internet, that was actually a thermal blanket lost during a 1998 NASA spacewalk, photographed tumbling away from the ISS. Other supposed sightings turned out to be discarded rocket boosters or fragments from old satellites, their irregular orbits making them appear to pace Earth in eerie patterns. Even the ancient alien connection unraveled under scrutiny. The carvings cited as proof were later identified as modern hoaxes, but here's where the story twists. In 2018, the U.S. government's previously classified CubeSat program revealed they'd secretly launched tiny, black-coated satellites during the Cold War to monitor Soviet communications, some of which did match descriptions of the Black Knight. Could decades of conspiracy theories have accidentally stumbled onto a grain of truth, a real-world spy satellite mistaken for extraterrestrial tech? It's a delicious irony. The Black Knight might not be alien, but it was hiding something. What makes this myth endure isn't just the allure of ancient astronauts, it's how perfectly it mirrors humanity's relationship with space. Every piece of drifting debris becomes a Rorschach test, reflecting our hopes, fears, and the eternal question: are we being watched? The Black Knight may never gallop through the stars as some envisioned, but in a way, it's done something even more remarkable, proving that sometimes the line between paranoia and prophecy is as thin as a thermal blanket fluttering in zero gravity. At Saturn's north pole, where most planets might host a swirling hurricane or a featureless haze, something geometrically impossible dominates the sky, a perfect hexagon, wider than Earth itself, with sides sharper than a razor's edge. This six-sided storm has raged for at least 4 decades, possibly centuries, its jet stream walls whipping at over 300 miles per hour without ever breaking form. Hurricanes on Earth dissipate in days, Jupiter's great red spot shrinks yearly, yet Saturn's hexagon defies all expectations, standing as one of the most precise natural shapes ever discovered in the cosmos. So how does a gas giant, a world without solid ground or oceans, sculpt a storm into a polygon? The answer lies in fluid dynamics pushed to extremes. On Earth, atmospheric patterns are chaotic, shaped by friction from mountains and oceans. But Saturn is a spinning ball of hydrogen, its atmosphere so deep and uniform that it behaves like a cosmic lab experiment. Scientists theorize the hexagon forms because of shear forces between different layers of Saturn's atmosphere, each moving at slightly different speeds. Like honey poured onto a spinning plate, the faster-moving equatorial jets collide with slower polar currents, creating stable waves, and under the right conditions, those waves can lock into precise angles. Here's the twist: laboratory experiments using spinning water tanks have recreated similar polygonal shapes, but none as persistent or massive as Saturn's. The hexagon's stability might come from something deeper, perhaps a cylindrical vortex plunging hundreds of miles into the planet's interior, acting like an invisible spindle that anchors the storm's geometry. Or it could be resonance, a rhythmic interaction between the planet's rotation and atmospheric waves, like a singer shattering a glass with the perfect pitch. What makes this phenomenon truly humbling is its exclusivity. Jupiter's poles host chaotic cyclones, Neptune's winds scream at supersonic speeds, yet nowhere else in the solar system does nature draft such a flawless geometric masterpiece. The hexagon isn't just a storm, it's a lesson in how simplicity can emerge from complexity, a reminder that even in the chaos of space, there's room for perfection. And until we send another probe through its enigmatic walls, this six-sided sentinel will keep spinning, a cosmic puzzle etched into Saturn's clouds. Human ingenuity has dreamed up countless ways to push against the void of space: rockets, ion drives, even light sails. But in the early 2000s, a group of engineers claimed to have cracked physics itself. The M drive, short for electromagnetic drive, wasn't just another propulsion concept. It promised thrust without propellant, movement without reaction, a literal free lunch that seemed to violate Newton's third law. For every action, there must be an equal and opposite reaction. The idea was simple, at least on paper. A microwave cavity shaped like a copper cone would bounce electromagnetic waves back and forth. Somehow, miraculously, this would create net thrust in one direction, as if the universe had forgotten to charge its usual toll. Initial tests by inventor Roger Scheuer in the early 2000s, and later by NASA Eagleworks lab, reported tiny but measurable thrust, mere micronewtons, barely enough to nudge a sheet of paper. But in the frictionless environment of space, even that could theoretically add up over time, enabling spacecraft to reach distant stars without hauling tons of fuel. The implications were staggering. Interplanetary missions could last months instead of years. Probes might reach Alpha Centauri within human lifetimes. The M drive became the underdog hero of spaceflight forums, a symbol of what might be possible if we dared to question the old rules. Then came the backlash. Critics pointed out that the measured thrust was suspiciously close to the margin of error, and that no one could explain how it worked without invoking new physics. The law of conservation of momentum wasn't just some bureaucratic regulation, it was woven into the fabric of reality. If the M drive worked, it would mean energy could appear from nowhere, or that microwaves were somehow pushing against the quantum foam of spacetime itself. Even Scheuer's own explanations shifted over time, ranging from relativistic effects to hand-wavy appeals to pressure differences in the cavity. The final blow came in 2021 when a team at Dresden University built a super-sensitive test rig, isolating the M drive from every conceivable external force. Their result, no thrust, at least none beyond what could be chalked up to thermal expansion, heated metal warping ever so slightly, mimicking movement. Other labs reached similar conclusions. The M drive, it seemed, was a mirage born from experimental error, wishful thinking, and the seductive allure of breaking the rules. Yet its legacy lingers. The M drive saga wasn't just about a failed experiment. It was a masterclass in how science should work. Extraordinary claims met extraordinary scrutiny. Hopes were tempered by hard evidence, and in the end, the universe won, as it always does. But for a brief, thrilling moment, we dared to imagine a world where the stars might be closer than they seemed. Beyond the orbit of Neptune, where sunlight is 1,000 times dimmer than on Earth, lies a cosmic junkyard of frozen leftovers from the solar system's birth, the Kuiper Belt. This sprawling ring of icy debris, home to Pluto and countless other dwarf planets, should theoretically stretch smoothly outward, its population gradually thinning as you move farther from the Sun. But something bizarre happens around 50 astronomical units out, a sudden, inexplicable drop in objects, as if someone drew a line in the cosmic sand. Astronomers call this boundary the Kuiper Cliff, and its existence defies everything we thought we knew about how planetary systems form. The numbers tell the story. Up to that 50O mark, Kuiper Belt objects KBO are plentiful icy worlds like Haumea, Makemake, and a sea of smaller bodies, but beyond it, the drop-off is staggering. Surveys find fewer than 1% of the expected objects, as if the belt's outer edge were sheared off by some invisible cosmic gardener. At first, scientists suspected observational bias. Maybe our telescopes just couldn't spot faint objects at that distance. But even the most sensitive instruments, like the Subaru telescope's wide-field surveys, confirm the cliff is real. The universe isn't playing hide and seek. It's left us a genuine mystery. So what could carve such a sharp edge? One leading theory points to an unseen planet, a hypothetical Planet 9 lurking hundreds of O away, its gravity sculpting the Kuiper Belt like an unseen hand rearranging marbles on a table. Computer simulations show how a distant super-Earth could shepherd objects into clustered orbits while clearing out a stark boundary. But there's a catch. After years of searching, no such planet has been found. The alternative, maybe the cliff is a fossilized scar from the solar system's violent youth, when Neptune migrated outward, flinging KBOs inward or ejecting them entirely. The trouble is, migration models struggle to explain why the cutoff is so precise. Why not a gradual decline? Then there's the wild card, interstellar intruders. Some researchers speculate that a passing star, long before humans walked the Earth, could have stripped the outer Kuiper Belt like a thief in the night. Others propose that the cliff marks the original edge of the solar nebula, the gas cloud that birthed our planets, where material simply ran out. But all these ideas have holes. If a passing star robbed us, why didn't it disturb the inner Oort cloud? If it's the nebula's edge, why don't other star systems show similar cliffs? The Kuiper Cliff isn't just a curiosity, it's a crack in the foundation of planetary science. Every explanation we've dreamed up feels like trying to fit a square peg into a round hole, leaving us with more questions than answers. Whether it's an unseen world, a cosmic accident, or something even stranger, this invisible boundary forces us to confront how little we truly understand about our own celestial backyard. And until we solve it, the outer solar system remains a place where the rules we've taken for granted suddenly and mysteriously stop applying. Deep in the heart of our Milky Way, where stars crowd so thickly they blur into a golden haze, there's a glow that shouldn't exist, an eerie excess of gamma rays, the universe's most energetic light, pulsing from the galactic center with no obvious source. This galactic center excess, first spotted by NASA's Fermi Gamma Ray Space Telescope in 2009, defies all expectations. It isn't coming from known objects like pulsars or black holes. It doesn't match the radiation patterns of cosmic rays colliding with gas. Instead, it forms a symmetrical, spherical halo around the core, like a ghostly beacon no one knows how to turn off. At first, astronomers thought they'd stumbled onto dark matter's smoking gun. According to leading theories, dark matter particles might annihilate when they collide, converting their mass into gamma rays. The Milky Way's core, dense with dark matter, would be the perfect place for this to happen. The glow's shape and energy matched some models perfectly. It could have been the first direct evidence of dark matter's true nature. But then the plot thickened. Detailed analysis revealed tiny point sources embedded within the glow, suggesting that at least part of the signal comes from something far more mundane. A hidden population of pulsars, the rapidly spinning corpses of dead stars. These aren't ordinary pulsars. They'd need to be millisecond pulsars, spun up to dizzying speeds by stealing matter from companion stars, emitting gamma rays like cosmic lighthouses. The problem, we've never observed enough of them to explain the excess. Either our current pulsar census is woefully incomplete, or these objects are somehow different, older, dimmer, or clustered in ways we've never seen. The debate rages on. Is this glow the whisper of dark matter's demise, or just a choir of unseen stellar remnants? The answer could reshape physics. If it's dark matter, we're glimpsing a particle that makes up 85% of the universe's mass. If it's pulsars, we've uncovered an entire hidden chapter of stellar evolution. Either way, the galactic center keeps its secrets for now. Every new telescope, from gamma-ray observatories to gravitational wave detectors, brings us closer to solving this high-energy riddle, proving once again that the universe's brightest mysteries often hide in plain sight. In the constellation Monoceros, where most nebulae swirl in elegant spirals or billow like cosmic smoke, one structure stands defiantly angular, the Red Rectangle Nebula. This celestial oddity, glowing with an eerie crimson hue, looks less like a natural formation and more like a geometric sketch drafted by some cosmic architect. At its heart lies not one star but two, a binary system locked in an intricate gravitational dance, their interactions sculpting the surrounding gas and dust into one of the most mathematically precise shapes ever observed in deep space. What makes the Red Rectangle so extraordinary is its ladder-like structure, a series of concentric rectangular shells radiating outward, as if the nebula were built from nested picture frames. This isn't just artistic happenstance, it's the result of stellar physics pushed to its limits. The central binary pair, HD 44179, consists of an aging star shedding its outer layers and a smaller companion that funnels this expelled material into twin cones. As the system rotates, these cones precess like wobbling tops, tracing out the edges of the rectangles over millennia. The result is a cosmic spirograph pattern, etched in glowing hydrogen and carbon-rich dust. The nebula's vivid red color comes from an equally rare phenomenon: fluorescent hydrocarbon molecules energized by the dying star's ultraviolet light. These aren't just any hydrocarbons, they're polycyclic aromatic hydrocarbons, or PAR, complex organic compounds more commonly found in soot or engine exhaust. How they formed in such abundance here remains a puzzle. Some scientists speculate the binary star's unique environment catalyzed their creation, while others suggest they're remnants of shattered comets or icy planetesimals, vaporized and reassembled in the nebula's turbulent winds. But the real mystery is why we don't see more structures like this. Most planetary nebulae, the glowing shrouds of dying stars, are chaotic and asymmetrical, their shapes dictated by random stellar winds or magnetic fields. The red rectangle's precision implies an almost freakish alignment of conditions, a binary pair with just the right spacing, mass, and orbital dynamics to sculpt order from chaos. Even more intriguing, this symmetry won't last. As the primary star continues to die, its eruptions will eventually overwhelm the delicate balance, transforming the nebula into something far more turbulent, a fleeting masterpiece in the universe's gallery of transient wonders. Perhaps the most haunting lesson of the red rectangle isn't just its beauty, but its rarity. In a cosmos that favors entropy and disorder, such perfection is the exception, not the rule. It's a reminder that even in the vast, impersonal void, celestial bodies can still conspire to create something briefly, breathtakingly precise, a geometric whisper in the relentless noise of deep space. Among the countless galaxies swirling through the cosmos, most fall into familiar categories: spirals with their graceful arms, ellipticals like fuzzy golden eggs, or ragged irregulars defying symmetry. Then there's Hoag's object, a celestial bull's eye so flawless it looks like it was painted onto the void by an obsessive cosmic artist. Discovered in 1950 by astronomer Art Hoag, this nearly perfect ring galaxy floats in isolation, its brilliant blue circle of young stars orbiting a golden central core like a diamond set inside a fiery halo. The strangest part, there's no visible bridge of stars or dust connecting the core to the ring, no messy evidence of a violent collision, just pristine, empty space between the two components, as if someone had carefully erased the scaffolding that built it. So how does nature craft something so geometrically pristine? The leading theory points to a galactic bullseye, a rare resonance ripple. Imagine dropping a pebble into a pond, but instead of water, the ripples move through a galaxy's reservoir of gas. When density waves pulse outward, they can trigger bursts of star formation in neat, concentric circles. But Hoag's object's perfect symmetry suggests something even more peculiar. It may be the aftermath of a smaller galaxy piercing dead center through a larger one billions of years ago, like a bullet through an apple. The impact would have sent shockwaves through the victim galaxy's gas, compressing it into a star-forming wave that propagated outward while leaving the central core untouched. Computer simulations show such collisions can create ring structures, but none as perfectly balanced as Hoag's. Then there's the instability hypothesis, the idea that the galaxy's own rotation tore it apart from within. If a rotating disk galaxy accumulates too much gas, it can become unstable, fragmenting into rings without any outside interference. This would explain the absence of a visible intruder nearby. But again, the math doesn't quite add up. Simulations struggle to replicate Hoag's razor-sharp edges and eerie symmetry without some external nudge. The plot thickens when you peer deeper into the void around Hoag's object. In 2021, astronomers discovered a second, fainter ring galaxy lurking even farther out, a cosmic doppelganger that might hint at an entirely unknown formation mechanism. Could both objects be the work of an ancient, unseen force, a primordial black hole's gravitational lensing, or a dark matter filament's invisible hand? Or is Hoag's object not a ring galaxy at all, but a rare polar ring galaxy viewed head-on, its perpendicular disk of stars masquerading as a perfect loop? What makes this galactic oddity so mesmerizing isn't just its beauty, it's the defiance. In a universe that thrives on chaos, Hoag's object is a rebel, flaunting precision where none should exist. Every new observation peels back another layer, revealing not just a cosmic mystery but a silent challenge. Sometimes the universe doesn't play by the rules we've written for it. And that's what makes Hoag's object more than an outlier. It's a cosmic whisper, reminding us that for every law we think we've decoded, there's always an exception waiting in the dark. If our universe were a canvas, the Hercules Corona Borealis Great Wall would be the boldest brushstroke, an almost unfathomable filament of galaxies stretching 10 billion light-years across the void. To put that into perspective, if you could travel at the speed of light, it would take you twice the age of Earth just to traverse its length. This isn't just a structure, it's a cosmic continent dwarfing everything else we've discovered. And here's the twist: according to our best models, it shouldn't exist at all. The story begins in 2013, when astronomers mapping gamma-ray bursts, the universe's most violent explosions, noticed an eerie clustering in the constellations Hercules and Corona Borealis. These bursts acted like cosmic breadcrumbs, tracing the outlines of something massive lurking in the darkness. As the data piled up, the truth became undeniable. They'd stumbled upon a wall of superclusters, galaxies, and dark matter so vast it challenged the cosmological principle. The foundational idea that, on large scales, the universe should look roughly the same everywhere. The scale is what defies belief. The Hercules Corona Borealis Great Wall isn't just bigger than previous record holders like the Sloan Great Wall. It's in a league of its own, spanning a tenth of the observable universe. Imagine finding a mountain range so tall it pierces the stratosphere, then realizing it's actually a single, connected ridge wrapping halfway around the planet. That's the level of cosmic audacity we're dealing with here. So how did this titan form? One theory suggests it's a relic of the early universe, a fossilized imprint of primordial density fluctuations that somehow avoided being smoothed out by cosmic expansion. Another posits that dark energy's repulsive force might have stretched certain regions into these mind-bending megastructures. But even these explanations feel like band-aids on a gaping wound in our understanding. The real puzzle isn't just its size, it's the timing. The wall's estimated distance puts its formation just a few billion years after the Big Bang, a period when the universe was thought to be too young and too homogeneous for such behemoths to assemble. Then there's the philosophical weight. If structures this colossal can exist, what does that say about the true scale of the cosmos? Are we staring at a statistical fluke, or the first hint of an even grander pattern, a fractal universe where walls concatenate into superwalls ad infinitum? The discovery forces us to confront an unsettling possibility. What we call the observable universe might just be a tiny corner of something exponentially more complex, a single tile in a mosaic whose full design we can't yet fathom. Every new survey peels back another layer of this enigma. Some researchers argue the wall might be an illusion, a chance alignment of smaller structures projected onto the same patch of sky. Others counter that its gamma-ray burst signature is too consistent to be coincidental. What's certain is this: the Hercules Corona Borealis Great Wall isn't just redefining the limits of cosmic structure. It's proof that the universe, for all our mapping and measuring, still has the power to leave us utterly humbled by its grandeur. Tucked away in the constellation Monoceros, just 1,500 light-years from Earth, lurks a cosmic paradox, the unicorn. This peculiar object holds the title of the closest known black hole to our solar system, but it's not the monstrous gravitational predator you might expect. Weighing in at a mere 3 times the mass of our Sun, the unicorn defies everything we thought we knew about how black holes form. Most stellar mass black holes we've discovered are at least 5 times heavier, the remnants of colossal stars that collapsed under their own weight. So how did this pint-sized singularity come to exist? The answer lies in the frantic dance of a nearby red giant star and a wobble that betrayed the unseen monster's presence. Astronomers first noticed something off about the red giant V723 Monocerotes. Its light exhibited subtle shifts in velocity, as if an invisible partner were tugging it back and forth in a cosmic game of tug-of-war. After ruling out planets or stellar companions, the math pointed to only one possibility: a black hole so lightweight it straddles the theoretical boundary between neutron stars and traditional black holes. This mass gap object shouldn't exist. Current models struggle to explain how a dying star could collapse into something so small without leaving behind a neutron star instead. Yet the unicorn's gravitational fingerprint is undeniable, its pull warping the red giant's motion like a hidden puppeteer. What makes this discovery even more extraordinary is how it was found. Unlike most black holes detected through violent X-ray flares, as they rip apart and consume nearby stars, the unicorn is a quiet neighbor, its appetite restrained. The red giant orbits just far enough to avoid being shredded, making this pair a cosmic odd couple. Their peaceful coexistence allowed researchers to study the black hole's mass through gravitational effects alone, pioneering a new way to hunt for these invisible predators. Now, astronomers suspect the galaxy could be teeming with similar, quiet black holes lurking undetected in binary systems. The unicorn's existence challenges decades of astrophysics. If black holes can form at such low masses, it implies stars might collapse in ways we've never witnessed, perhaps through exotic processes involving magnetic fields or rapid rotation. Some theorists even speculate these mini black holes could be primordial, forged in the chaos of the Big Bang itself rather than from dying stars. Whatever its origins, this cosmic unicorn is more than a curiosity. It's a key that might unlock entirely new chapters in our understanding of stellar death and the hidden population of black holes silently shaping our galaxy. For years, the barren plains of Mars have whispered a tantalizing secret, a gas that, on Earth, is almost synonymous with life: methane. Since NASA's Curiosity rover landed in Gale Crater in 2012, its onboard instruments have sniffed out sporadic spikes of this elusive molecule, sometimes hitting concentrations 10 times higher than background levels. These detections come and go like ghostly signatures, vanishing as suddenly as they appear, leaving scientists locked in a fierce debate. Is this methane the fingerprint of hidden Martian microbes, or just the echo of ancient geology? The intrigue lies in methane's dual nature. On Earth, the vast majority of atmospheric methane comes from biological sources: belching cows, decomposing wetlands, even the metabolic activity of microorganisms. But it can also be produced abiotically through chemical reactions between water, carbon dioxide, and certain rocks like olivine, a process called serpentinization. So when Curiosity's tunable laser spectrometer caught those fleeting methane whiffs, the question became unavoidable: which Mars are we seeing? A world where subterranean microbes might still eke out an existence, or one where sterile chemistry mimics the signals of life? The mystery deepens with the methane's erratic behavior. Unlike Earth, where methane lingers for years, Mars' thin atmosphere and intense ultraviolet radiation should break it down within centuries. Yet Curiosity's data shows fluctuations on a timescale of weeks or even days, suggesting an active, ongoing source. Some researchers argue this points to localized reservoirs, perhaps underground pockets where microbial communities persist in briny aquifers, releasing gas through cracks in the surface. Others point to seasonal variations, where temperature changes trigger the release of trapped methane from icy clathrates or porous mineral structures. Then there's the orbital contradiction. While Curiosity detects these transient spikes, the European Space Agency's Trace gas orbiter, equipped with far more sensitive methane-sniffing instruments, has largely come up empty. One theory suggests the orbiter's daytime measurements miss the methane, which might dissipate quickly under sunlight, while Curiosity samples the air at night. Alternatively, the methane could be breaking down faster than expected, or seeping out in such narrow plumes that satellites simply fly right past them. The stakes couldn't be higher. If the methane is biological, it would be the most compelling hint of extraterrestrial life in history. If geological, it still reshapes our understanding of Mars as a geologically active world, with reservoirs of liquid water or hydrothermal systems lurking beneath the dust. But until another mission, like the Mars Life Explorer or a dedicated methane-sniffing drone, can pinpoint the source, this enigma will keep us guessing. Every new detection is a riddle wrapped in a mystery, floating just beyond our reach in the thin red air. At the farthest reaches of our solar system, beyond the icy orbits of Neptune and Pluto, something massive seems to be warping the paths of distant objects, a gravitational puppeteer we've never seen. This is the tantalizing premise of Planet 9, a hypothetical world up to 10 times the mass of Earth, lurking in the frigid darkness of the outer solar system. The clues started piling up in 2014, when astronomers noticed something odd about the orbits of extreme trans-Neptunian objects, icy bodies like Sedna and Biden that swing hundreds of astronomical units from the Sun. These objects shouldn't cluster together, their paths should be random. Yet 6 of them aligned like cosmic clockwork, their orbits tilted and stretched as if tugged by an unseen hand. The math points to something extraordinary. Simulations show a distant planet could shepherd these objects into their peculiar configurations. Planet 9's proposed orbit would be elliptical and tilted, taking it 15 to 20 times farther from the Sun than Neptune at its most distant point. A single year on this world might last up to 20,000 Earth years, but how could something so big remain hidden? Part of the answer lies in distance and darkness. Even at its closest approach, Planet 9 would reflect barely any sunlight, appearing 100,000 times dimmer than Pluto. Current telescopes would struggle to spot it unless they happen to look in exactly the right place at the right time. The search has become a modern-day celestial treasure hunt. Teams scour archival data from observatories like Pan-STARRS and Subaru, looking for faint streaks moving against the stars. Other researchers use indirect methods, tracking gravitational anomalies in the orbits of known objects or hunting for heat signatures in infrared surveys. In 2021, a study suggested Planet 9's influence might even explain why the solar system's plane is tilted by 6 degrees, a puzzle that's lingered since the 1970s. Yet not everyone's convinced. Some scientists argue the orbital clustering could be a statistical fluke or the collective gravity of many smaller objects. Others propose an alternative culprit, a primordial black hole no bigger than a grapefruit but with the mass of a planet, warping space-time invisibly. The truth remains tantalizingly out of reach, but the hunt continues. New telescopes like the Vera Rubin Observatory, set to begin scanning the skies in 2025, could finally settle the debate, either by spotting Planet 9 directly or ruling it out entirely. What makes this mystery so compelling isn't just the potential discovery of a new planet, it's the reminder that our solar system might still hold colossal secrets. Whether Planet 9 turns out to be a frozen super-Earth, a rogue world captured from another star, or something even stranger, its mere possibility forces us to reconsider how much we truly know about our cosmic neighborhood. After all, if something this massive has eluded us for so long, what else might be hiding in the dark? Most stars go out with a bang, a supernova so violent it obliterates them completely, leaving behind only a neutron star or black hole. But deep in the cosmic archives, astronomers have found celestial rebels that refuse to die cleanly. Meet the zombie stars, white dwarfs that endure their own explosions, limping away from supernova like cosmic undead. The most puzzling of these survivors belong to a class called Type Ix, explosions so weak they've been dubbed mini-supernova, where the star partially detonates but somehow clings to existence, defying everything we thought we knew about stellar death. The mystery starts with how these explosions ignite in the first place. Ordinary Type Ia supernova occur when a white dwarf, the dense core left after a star like our Sun, exhausts its fuel, steals enough mass from a companion star to cross a critical threshold, triggering a runaway thermonuclear explosion that tears the dwarf apart atom by atom. But Type Ix events are different. They're fainter, slower, and leave behind a bizarre remnant, a scarred, still smoldering white dwarf that somehow survived the blast. Imagine lighting a stick of dynamite only to find half of it stubbornly intact after the smoke clears. That's the level of defiance we're dealing with here. So how does a star cheat death like this? One theory suggests these explosions might be failed supernova, where the thermonuclear flame front sputters instead of racing through the entire star. Picture trying to light a damp log. It might burn unevenly, leaving chunks uncharred. Alternatively, the white dwarf could be spinning so rapidly that centrifugal force prevents a complete explosion, like a merry-go-round flinging off sparks but staying intact. Some models even propose that the companion star isn't a normal star at all, but another white dwarf, merging in a way that triggers only a partial detonation. The aftermath is just as puzzling. Survivors like the star LP40-12, which bears the chemical scars of a past explosion, glow with unusual compositions, layers of silicon, sulfur, and iron forged in the blast, yet still clinging to a coherent structure. Others, like the remnant at the heart of supernova 2002CX, flicker erratically, their light curves suggesting a fractured, unstable object trying to regain equilibrium. These aren't just damaged stars, they're cosmic test cases forcing us to rewrite the rules of stellar physics. What makes zombie stars truly unsettling is what they imply about the universe's flexibility. If white dwarfs can endure supernova, how many other stellar deaths have we misinterpreted? Could some supernova leave behind even stranger remnants, stars stripped down to exotic quark matter, or hybrid objects that blur the line between white dwarfs and neutron stars? Every new discovery peels back another layer, revealing a cosmos far more unpredictable than our textbooks dared to suggest. One thing's certain, in the grand story of stellar life and death, the final chapter might be a lot messier and a lot more interesting than we ever imagined. Somewhere beyond the edge of everything we know, an invisible force is pulling at the very fabric of the cosmos, not gently, but with enough strength to drag entire clusters of galaxies toward an unfathomable destination. This is the dark flow, one of the most unsettling discoveries in modern cosmology. It started in 2008 when astronomers noticed something impossible while studying microwave background radiation, the afterglow of the Big Bang. Galaxy clusters weren't just drifting randomly with the expansion of the universe. They were all streaming in the same direction at nearly 2 million miles per hour, as if caught in a cosmic undertow leading somewhere beyond our observational horizon. The culprit, whatever it is, it can't be part of our observable universe. All known gravitational influences, superclusters, dark matter halos, even the Great Attractor, are accounted for. This motion suggests something colossal lurking in the unseeable beyond, a structure so massive its gravity ripples across spacetime like a ship's wake. The leading theory that we're feeling the gravitational tug of another universe entirely, a neighboring bubble in the multiverse brushing against our own like soap suds in a sink. Not everyone's convinced. Skeptics argue it could be a statistical fluke or an artifact of how we measure cosmic microwave background, but the evidence keeps mounting. Recent studies tracking thousands more galaxy clusters found the flow extends at least 2.5 billion light-years, far too vast for any known structure. If confirmed, this isn't just a new object to catalogue, it's a crack in the foundation of how we define reality. Suddenly, the observable universe might be just our local neighborhood, with entire other realms hovering just out of sight, shaping our destiny from the shadows. What makes the dark flow so haunting is how it forces us to confront the limits of human perception. We're like fish in a pond, unaware of the ocean beyond its shores. Yet here, in the silent drift of galaxies, we might be seeing the first fingerprints of something infinitely larger. A cosmic web stretching farther than light has had time to travel since the dawn of time. Whether it's proof of parallel universes or something even stranger, one thing's clear: the cosmos doesn't end where our telescopes do, and whatever's out there, it's pulling us toward answers we're not even sure how to ask for yet. Imagine measuring the same room with two different rulers, yet each time you get wildly different results. That's essentially the crisis cosmologists are facing with the Hubble tension, a stubborn discrepancy in one of the most fundamental numbers in the universe, how fast space itself is expanding. On one side, we have meticulous measurements of the early universe's afterglow, the cosmic microwave background, suggesting an expansion rate of about 67 kilometers per second per megaparsec. On the other, observations of nearby stars and supernova peg the number closer to 73. That 6-unit gap might sound trivial, but in the precision-driven world of cosmology, it's enough to keep scientists awake at night, questioning whether we've misunderstood the universe's very foundation. The stakes couldn't be higher. The expansion rate, dubbed the Hubble constant, isn't just a number, it's the yardstick for everything from the age of the universe to the fate of galaxies. For decades, astronomers assumed these two measurement methods would eventually converge. Instead, as telescopes like Hubble and Planck collected better data, the gap widened. It's as if the universe's early childhood diary and its adult memoir tell irreconcilable stories, forcing us to ask, did something change over cosmic time, or are we missing a hidden character in the plot? One tantalizing possibility is that dark energy, the mysterious force accelerating the universe's expansion, isn't constant after all. Maybe it evolves, growing stronger or stranger as the cosmos ages. Alternatively, there could be an undiscovered particle, like a dark radiation, that subtly influenced the early universe's expansion but faded from view. Some theorists even entertain wilder ideas, like a temporary kick from a primordial black hole collision or a flaw in Einstein's gravity that only manifests across cosmological distances. But the most unsettling scenario, that the discrepancy is real and our universe isn't as uniform as we thought. Recent galaxy surveys hint at subtle variations in expansion rates depending on direction, a potential cosmic tilt that could mean space itself is lopsided on grand scales. If true, it would upend the cosmological principle, the bedrock assumption that the universe looks roughly the same everywhere. Suddenly, our corner of the cosmos might be special after all, not in location but in texture, a wrinkle in spacetime's fabric we're only now beginning to sense. The race to solve this puzzle is heating up. Next-generation telescopes like the Nancy Grace Roman Space Telescope aim to measure the Hubble constant with unprecedented precision, while lab experiments hunt for signs of exotic particles that could bridge the gap. Whatever the answer, the Hubble tension isn't just a technical glitch, it's a cosmic crossroads, forcing us to choose between tweaking our models or rewriting them entirely. And that's the beauty of it. In science, the most terrifying crises often become the most transformative breakthroughs. After all, the universe isn't obliged to make sense, but we'll never stop trying to make sense of it. From black holes that bend the rules of physics to galaxies spinning in impossible ways, these 30 cosmic enigmas prove one thing: the universe is far stranger, wilder, and more mysterious than we ever imagined. Each phenomenon we've explored, from the eerie whispers of the wow signal to the galaxy-sized perfection of Hoag's object, is a reminder that no matter how much we learn, the cosmos always has another puzzle waiting in the dark. Think about it, dark matter silently shaping galaxies, quasars blazing with the light of 1,000 suns, entire voids in space where galaxies should be but aren't. These aren't just oddities, they're cosmic breadcrumbs leading us toward questions we haven't even thought to ask yet. And that's the beauty of astronomy. The more we discover, the more we realize how much we don't know. But here's the best part: you get to be part of this grand adventure. Every time you look up at the night sky, you're staring into the same unknowns that have fascinated humanity for millennia. Maybe the next big breakthrough will come from a backyard telescope, a classroom discussion, or even a comment left on a video like this one. The universe doesn't give up its secrets easily, but that's what makes the hunt so thrilling. So keep wondering, keep questioning, and most importantly, keep looking up. If you've enjoyed this cosmic journey through the universe's greatest unsolved mysteries, make sure to subscribe and hit that notification bell. We've got plenty more celestial deep dives on the way, from the strange physics of neutron stars to the mind-bending possibilities of parallel universes. And drop a comment below which of these 30 phenomena blew your mind the most. Is there a cosmic mystery we missed that keeps you up at night? The universe isn't done surprising us yet, and neither are we. Until next time, stay curious, fellow stargazers. The cosmos has plenty more secrets to share.